Welcome to Mootechie, your go-to place for science made simple and smart. In today's session, we're exploring physical properties related to heat transfer, a key topic in food and process engineering. Let's begin moving slide by slide. Moving to next slide. Introduction. Physical properties are needed in process design, for estimating other properties, and for product characterization or quality determination. The movement of heat to and through a food material depends primarily on the existence of a temperature difference and on physical characteristics such as size, shape, density, and thermal properties. The thermal properties are unique for each food. Each mechanism of heat transfer has an associated thermal property. In simple words, the way heat travels through food depends a lot on its structure and unique characteristics. Moving to next slide. Water content. The moisture content of a food material is the quantity of water it contains. Moisture content in wet basis equals initial wet weight minus final dry weight divided by initial wet weight multiplied by 100. Moisture content in dry basis equals initial wet weight minus final dry weight divided by final dry weight multiplied by 100. Thermal properties are strongly influenced by the water content and to a lesser degree by temperature and pressure. That means water plays a huge role in how food heats up or cools down. Moving to next slide. Specific heat. Specific heat, also called heat capacity, is the heat required to increase the temperature of one unit of mass by 1 degree. Its unit is joules per kilogram Kelvin. Siebel's formulas help calculate it. Above freezing, Cp equals 3.35 times water plus 0.84. Below freezing, Cp equals 1.26 times water plus 0.84. So the more water a food has, the more heat it takes to warm it. Moving to next slide. Thermal conductivity. Thermal conductivity is how easily heat flows through a material. It's the amount of heat passing per unit time, area and temperature gradient. Unit watts per meter Kelvin. There's also an equation using food composition. K equals 0.25 times carbohydrate plus 0.155 times protein plus 0.16 times fat plus 0.135 times ash plus 0.58 times water. This means water and other food components affect how well heat spreads inside. Moving to next slide. Effect of temperature on thermal conductivity. In good conductors, conductivity decreases with temperature due to resistance to electron flow. In insulators, conductivity increases with temperature because of more atomic movement. In gases, it increases due to more random molecular activity. Different materials behave differently as temperature changes. Moving to next slide. Thermal insulation. To save heat energy, equipment must be insulated. Insulating materials should have low thermal conductivity. This is achieved by trapping air or gases in tiny spaces inside solids or by using loose solid particles. The insulating effect depends on both the material and the gas inside. Moving to next slide. 3 types of insulating materials. Fibrous. Small filaments like mineral wool, loosely packed, used below 700 degrees Celsius. Cellular, foam boards like polyurethane and polystyrene with air pockets. Granular, small grains or flakes of inorganic material formed into shapes. Each of these traps air differently to stop heat flow. Moving to next slide. Thermal resistance. Thermal resistance helps understand heat flow. Unit, degrees Celsius per watt. Its inverse is thermal conductance. Conduction resistance equals thickness divided by conductivity times area. Convective resistance equals 1 over convection coefficient times area. Radiative resistance includes surface factor and temperature terms. Each mode of heat transfer has its own way to measure resistance. Moving to next slide. Thermal diffusivity. This is important when temperature changes with time and location. It combines conductivity, density, and specific heat. It's defined as heat conducted divided by heat stored per unit volume. Unit meter squared per second. Formula: alpha equals K divided by rho times Cp. Moving to next slide. Convective heat transfer coefficient. This describes how much heat is transferred for a given temperature difference and area per unit time. Q equals HA times the temperature difference. The coefficient ranges from 3 watts per square meter per degree Celsius for still air up to 100,000 for condensing steam. Moving to next slide. Convective heat transfer coefficient continued. Unlike thermal conductivity, this value depends on fluid speed, fluid properties, surface texture, and object shape. There are no standard values for all situations. Dimensional analysis is used to estimate it, and experience helps choose the correct value in real applications. Moving to next slide. Latent heat. Heat transfer may involve sensible or latent energy. If temperature changes, it's sensible heat. If a phase change occurs, like ice melting, it's latent heat. Latent heat involves energy exchange without temperature change. Moving to next slide. Heat of fusion. This is the energy exchange during the change from liquid to solid or vice versa. For example, freezing water into ice or thawing it back to liquid. It's a type of latent heat related to the solid-liquid phase transition. Moving to next slide. Latent heat of vaporization. This is the energy needed to turn a liquid into vapor. It's used in drying or evaporation. Vaporizing water helps remove moisture from food, but drying is energy intensive. Heat of vaporization is 7 times more than heat of fusion, and 5 times more than heating by 100 degrees Celsius. Moving to next slide. Boiling point rise. Boiling point increases when solutes are present in a liquid. It's higher than the boiling point of the pure solvent. This is common in foods with salt or sugar. Examples: processed meats and syrups. It's useful in evaporation and drying. Moving to next slide. Freezing point depression. Food freezes at lower temperatures than pure water. This is because of dissolved solids. The more solids, the lower the freezing point. Knowing the exact point helps control freezing and thawing processes. Moving to next slide. Radiative properties. When radiation hits a surface, part is absorbed, part reflected, and part transmitted. Absorptivity plus reflectivity plus transmissivity equals 1. Types of bodies. Black body absorbs all, alpha equals 1. Opaque body reflects and absorbs, no transmission. White body reflects all. Gray body has balanced properties across all wavelengths. Moving to next slide. Table of radiative properties. A summary table shows values for different materials. This helps in calculating radiation heat transfer accurately. Each surface behaves differently under radiation. Thanks for watching Mootechie. We hope this video helped you understand the physical properties related to heat transfer clearly and confidently. Don't forget to like, share and subscribe for more insightful content. Until next time, keep learning and stay inspired.